Hello, everyone. Welcome to the Invasive Mussel Collaborative webinar, Control Options for Irrigation Systems. My name is Erica Jensen. I'm a program manager with the Great Lakes Commission, and on behalf of the Invasive Mussel Collaborative, I want to thank you all for participating in our webinar today. For those of you unfamiliar, the Invasive Mussel Collaborative is identifying opportunities to advance scientifically sound technology for management and control of invasive Dreissenid mussels in order to produce measurable ecological and economic benefits. The collaborative provides a framework for communication and coordination and is working to identify the needs and objectives of resource managers, prioritize supporting science, and align science and management goals into a common agenda. If you would like to know more about the Invasive Mussel Collaborative, we encourage you to visit our website at www.invasivemusselcollaborative.net. The website is intended to serve as a central hub of information on Dreissenid mussels, and it includes background information on the collaborative, recordings of past webinars, and other information. If you know of information or have resources you would like to see posted to the website, please contact us. If you have not done so already, we also encourage you to join our Invasive Mussel email listserv. On the listserv, you will receive webinar announcements, read about recent Dreissenid-related news, and be able to connect with other researchers and managers. A link to join the email listserv is provided on our website. Today's webinar is part of an ongoing series of webinars hosted by the collaborative, and the purpose is to facilitate learning and information sharing on topics of common interest. The webinar will be recorded and archived with past and future webinars on our website. Today, we're pleased to have presentations from R&T Consulting, Agriculture and Agri-Food Canada, Alberta Agriculture and Forestry, and ZM Controllers. Our first presentation will provide an overview of control options and considerations in irrigation systems, and then we will explore two case studies in planning and execution, and we'll wrap up with a brief presentation on new technology that's being developed for control. Following the four presentations, we will have time for question and answers with webinar attendees. Before we begin the presentations, I'd like to cover a few additional logistical items about today's webinar. Given the large number of attendees registered for the webinar, all attendees' lines are on mute, and they will remain muted throughout the webinar. We will be taking written questions throughout the webinar, so if you have a question, you may type it into the questions pane of the GoToWebinar dashboard. You may submit questions at any time during the webinar, and depending on how we're doing on time, we may answer one or two questions following each of the presentations. However, we will likely hold all of the questions till the end of the webinar, and we'll address after all of the presentations have been given. We'll do our best to take all of your questions and comments during the webinar. If you have to leave before we have gotten to your question, we encourage you to review the recording that will be posted on our website to hear your question addressed at a later time. If you are experiencing any technical difficulties, you may send a chat directly to one of the Great Lakes Commission staff listed as organizers for this webinar, but hopefully that will not be a problem. So with that, I would like to introduce our first presenter for this webinar. Renata Claudi is an environmental scientist with over 30 years of diverse technical experience, much of it focused on macrofouling control in industrial systems. Currently, she is the president of her consulting company, R&T Consulting, Inc. Most of the assignments undertaken by the company focus on various aspects of aquatic alien species, and this includes work on economic impacts, selection and installation of appropriate control options, custom research and vulnerability assessments for various facilities. Most of the work in the last 5 years has involved the impact of quagga mussels on various facilities in the western U.S. and Canada, and custom research on innovative control options. Ms. Claudi has also co-authored a book titled Monitoring and Control of Macrofouling Mollusks in Freshwater Systems, issued by CRC Press. It's the latest in a series of publications, and she has been one of the organizers of the International Conference on Aquatic Nuisance Species since it was launched in 1990. So welcome, Renata, and thank you for providing this presentation today. We should be handing off presentation privileges to you right now.
Well, thank you very much. And hello, everybody. Good afternoon. I have quite a lot of material to cover, so I'm going to launch right in. And for those, because I don't know who's out there listening, I'm going to do a very quick review on the zebra and quagga mussels. They are part of the Dreissenid family of freshwater mussels. The particular problem, or at least the problem they pose to a man-made system, is that they can attach to substrates, which they are the only mussel in freshwater that does this. They're filter feeders, and they also have a free-swimming larva that stays in the plankton for up to 3 weeks, which also presents a set of problems that we have not seen before. The means of attachments is through byssal threads, which are shown here on the adult mussel. They're individual strands of sclerotized protein. When you look at them under a scanning electron microscope, you see that this is a very robust structure. Each one of the threads is attached to the substrate with a sticky pad. Most of the time when you remove the adult from the surface, either because they die or because you manage to pull them off, the byssal thread stays behind to sort of cause furry substrate on the materials of attachments. The life cycle, as I mentioned, has a 3-week period during which the larvae are in the plankton. There is external fertilization, and then there is various steps of development for 3 weeks through the plankton. When the larva becomes too large and too heavy, it reaches the pedivelager stage, sinks, and metamorphoses into an adult. During this 3-week period, they can be dispersed widely. They can penetrate into a number of systems and set up shop there. And they can be transferred in ballast water, in bilge, in live wells, and so on. So those are the problematic characteristics of the two species. How do you tell them apart, the zebra versus the quagga mussel? Well, it is said that all the zebra mussels, if you sit them up on a desk, will sit up straight, as you see on the left-hand side, and the quaggas will fall over because of the convex underside that they have. Also, when you're looking at the shell, where the two shells meet, in zebra mussels, it's a nice straight line. In quagga mussels, there is a wowie. Also, the quagga mussels, they tend to have one side of the shell slightly bigger than the other. So they're not quite symmetrical, and that actually is true even at the velager stage. Now, anybody that is considering or that is expecting an invasion of Dreissenid mussels really needs to, at the very least, look at the water quality of their system and see how much calcium there is present in the water, and also what the pH profiles look like during the year. Because calcium and pH are really the two variables that will determine if the Dreissenid mussels will do well in your system, or if they will have a small population, or if they will fail altogether. Once you have established if calcium and pH are actually in the range that the mussels would survive, it is quite important to actually look at the interplay of the two. We were able to put together calcium and pH variables through a number of lakes in North America where mussels both thrived and actually failed, to see what interplay of those two variables is able to support a population and which is not. So I encourage everybody who's worried about mussels invading their system to actually look at these two variables to give them some idea how much of a problem this population potentially could be. Apart from the calcium and the pH, which are sort of the founding variables, very low dissolved oxygen levels, below 5 milligrams per liter, which happens quite a lot in lots of reservoirs in the lower levels, will prevent successful development of velagers in those areas. Equally, very high or very low turbidity, as measured by Secudisc, will tell you if there is likely to be enough food for the mussels to eat. That's if the Secudepth is less than 8 meters, or if the turbidity is so high that the velagers are likely to caught up in the floc that's in the water, the filamentous algae, and basically have some problems developing. So very high and very low SECI depth is also something is worth considering as when you're evaluating how big a population might result in your body of water. The last variable that I want to talk about is the average water temperature in the summer. If it's below 17 degrees centigrade, it's probably not likely that development of gametes is going to take place, or there's going to be successful spawning. And if the average temperatures are above 29 degrees centigrade, it is very likely that the velagers will fail because it's going to be too hot. So these are the variables to consider if you are evaluating if the mussels will be able to succeed in your particular neck of the woods. Here is just a quick illustration of the water temperature. This is from Columbia River down near Renata Dam, and you can see that the temperature rises above the minimum required for reproduction, sometimes in June, maybe even later, and there is a very short period of temperature where the mussels will be able to reproduce and the velagers will succeed, and then it falls off again. So this gives you some idea on the length of the breeding season based on temperature. Now, the risks that are posed by zebra mussel fouling or clogger mussel fouling, obviously there is decrease of flow in system due to increased coefficient of friction. There is some potential plugging of components and nozzles, irrigation nozzles with primary settlement, and also shell debris. And then there is the impact on instrumentations which are in contact with raw water. We have seen this in the aqueducts in the south of the United States, where these instruments became quickly colonized by mussels, and basically they were not giving the right readings. So we do encourage people who are expecting mussels to come in when they are changing instrumentation to keep this in mind, and if possible change to non-contact instrumentation. So overall, how do we minimize the impact of dry-scented mussels? Well, the two basic choices is, are you going to prevent the settlement, which means you're going to be going after the velagers, or are you going to allow the velagers to settle, become adults, and then clean them out either periodically or at the end of the season? What you choose is really depending on the vulnerability of the system, how robust it is, how much fouling it can take, how you operate the system, what is the likely size of the mussel population based on the environmental variables? What is the maximum size an individual can reach at the end of the summer based on amount of food, temperature, and so on? And what is your operational preference and economic consideration under which you're operating? So given all these different tools that I'm going to be speaking about, this is the kind of decisions that every single person who has to deal with mussel will have to make. Obviously, mechanical cleaning is something that everybody is familiar with. You can either dewater and then use power wash to get rid of mussel shells. If you cannot dewater, then underwater use of divers, scraping, or vacuuming is also done extensively. Pigging of pipelines, that means introducing an abrasive plug into the pipeline and then pulling it through, is also done on fairly regular basis, particularly for drinking water plants. And it is successful provided that the pipeline that you're pigging is robust enough to take the outward pressure of the pig. Desiccation, which means dewatering and allowing the mussels to basically dry up, is something that has been done extensively in the southern United States. You have some examples here of the temperatures and the number of hours that you need to expose mussels to the air at those temperatures. It is somewhat also dependent on humidity, so desiccation definitely does work, and it's just a question of how long you can keep it up. If you cannot dewater, then the use of hot water washes is being used quite extensively in power plants, where they recirculate the warm water discharge till they get to the magic temperature, which starts killing the mussels. It is very effective. It is not without problems for the power plant, but it does work very well. Now, in Canada in particular and northern United States, freezing is probably one of the best friends we have, especially for irrigation system. As you can see, -3 degrees, which is really quite modest for 10 hours, is likely to kill all mussels in dewatered situations. Oxygen deprivation is something people speak about, but we actually haven't seen it used very much. Oxygen deprivation leads to a bunch of other problems, such as black, smelly water, so we haven't seen it being used very frequently at all. Now, besides the options we just described, non-oxidizing chemicals and oxidizing chemicals as well can be used to eliminate mussels either periodically or at the end of the breeding season. In terms of non-oxidizing chemicals, the ones that have been making the most headway is copper-based aquatic herbicides, some means of pH adjustment, Zequinox, which is a biopesticide, and it's a product of a dead bacterium, and potassium salts. So I will spend a little time on each one of these. Copper-based aquatic herbicides are great because they have already had, in most cases, a drinking water approval, or they are approved for drinking water. They have been used in reservoirs and aqueducts for control of algae. Basically, you are trying to get as much copper ion in a sort of chelated state so that it's very active, as close to the mussels as possible. One of the manufacturers is currently pursuing a Canadian label after obtaining a label in the United States for treatment of mussels. That particular product is from EarthTech, and it's called QZ. And here is some idea of how much copper you need for how long to eliminate adult mussels. Again, how much you need for how long is largely dependent on the ambient temperature. The more active the mussels are in the warmer water, the faster the copper is going to do them in. As the water cools off, the metabolic rate falls off, and it takes much, much longer. So as you can see here, 57 parts per billion at 20 degrees resulted in 100% mortality in 11 days. 30 parts per billion was having trouble getting 80% mortality in 19 days when the temperature was between 10 and 15 degrees centigrade. So as with most of the other control strategies, they do work better in warm water. However, copper is very effective. pH adjustment, and in this case, it's something that is below 6.9, is based on the fact that the dry-scented mussels actually have a very narrow tolerance to low pH. The fact that when you adjust the pH in water, it tends to persist for quite a long time, unlike oxidizing chemicals that can disappear within hours. Lower pH in general is not considered to be a problem for drinking water plants. They quite like it because the chlorine becomes a much more effective biocide for sterilization. And also, it does not seem to be a problem in terms of agricultural use of fish. In fact, talking to some of the agricultural people in Leamington, they quite like lower pH water. They think that it makes the nutrients more bioavailable to their crops. Now, you can use pH adjustment several different ways. The first one would be to get rid of the mussels at the end of the season. For that, you need to actually drop the pH down to a very low level. As you can see here, pH of 3 cause complete mortality in 96 hours in adult zebra mussels. That is quite a big adjustment, and people are somewhat uncomfortable about dropping the pH that low in terms of materials of construction, but in the right circumstances, it can be very effective. If very low pH is not something you want to practice, you can also use pH adjustment proactively. In this case, we were able to adjust the pH of incoming water, which had lots of veligers in it, to 3 different levels. And basically, as soon as we adjusted that pH down to 7.1, we stopped seeing settlement. So between 7.1 and 6.9, there was no settlement of veligers happening in that system. We also exposed a number of adult mussels in that same environment. And basically, even with that modest adjustment down to 6.9, we got 40% mortality of adults after 12 weeks of exposure. Now, these were quagga mussels, And this is what they looked like after 12 weeks. As you can see, the individuals on the left were definitely dead. There was no flesh left. The individuals on the right, there was still some flesh, so we kind of said, you are still alive, but possibly we were being a little too conservative. A lot of them were dead, but didn't know it. So that was very successful. Surprisingly, when we repeated this experiment in another location with only zebra mussels, we found that although we were able to prevent settlement, we were not able to induce the same kind of mortality in adults as we did in quagga mussels. To date, that is probably the biggest difference between the two species that I have observed, and it's very interesting. It seems that the zebra mussels are able to hold on to the calcium in their shells just a little better than the quaggas. Moving on, potassium salts, something that people have discussed for the use in irrigation system extensively because you're using potash for fertilization quite often. So if you can actually use potash to also eliminate mussels, you're getting 2 for 1. Again, as with all the other control strategies, you can use a lot for a short period of time, a little less for a little longer. So when you go above 200 parts per million of potassium chloride at 20 degrees, you get very swift mortality, probably in 48 hours. If you drop it down to 100 ppm, you're looking at 4 to 10 days, depending on the temperature. What we don't know is what it would take to actually prevent settlement. What would have to be the chronic exposure limit to potassium chloride for villagers not to settle and thrive? We think it's somewhere between 20 and 30 parts per million, but we have not done that experiment, and I'm sincerely hoping that somebody does. The one thing I want to mention about potassium salts is that some of the recent studies that we have done using potassium on Lower Colorado River showed that potassium was not nearly as effective there as it was on the Great Lakes. And we narrowed it down to the presence of sodium in the water. And basically, if you have a relatively high level of sodium in the water, your potassium will not be nearly as effective. So at the 100 parts per million, where in the Great Lakes water you're getting mortality between 4 and 10 days, we were waiting up to 30 days to get the same effect in water with higher sodium levels. So again, it really is important that you know what your water quality is and what's in it. Zequinox, it's the only biopesticide available for invasive mussel control. It's derived from a soil bacterium. It doesn't seem to have any effect on non-target organisms. It's very effective against dry senates. And it can be used either proactively as a sort of daily or weekly treatment, or at the end of the season to eliminate mussels. It is fairly expensive. It does increase the turbidity of the water, but it is very highly selective for dry senates. It is improving all the time, and it is definitely one of the really good tools in the toolbox. So besides the 4 chemicals that I described in details, there is all these other oxidizing chemicals that can be used at the end of the season. In irrigation systems, probably not as helpful unless you are already using one of these oxidizing chemicals for biofilm control. Because if you're doing biofilm control, then you could be using the same chemical for control of dry senate mussels. How long does it take to kill the mussels? Again, it's very much temperature dependent. We usually say about 2 weeks when the water is not too warm, because oxidizing chemicals are considered to be noxious. The mussels close down, and it's only when they have to reopen that they are exposed to the chemical. But we have seen mortality as quick as 4 days when the water was above 25 degrees centigrade. So as an end-of-season treatment, if you're also treating for biofilm, this could be something quite viable. Now, besides chemicals in pipelines, there is also a number of fixed screens and gates and concrete structures associated with irrigation systems. There are some very effective coatings that are available. They come in 2 flavors. One is the non-toxic soft silicone barrier coatings, which nevertheless have performed very well for up to 10 years. And then there is the copper-based toxic coatings that ablate and are also very effective. Many coatings fail after 12 to 18 months. So if you're going to be considering coatings, do ask for a long-term performance from the manufacturers. They should last 7 to 10 years because they are really very expensive and they require a great deal of work to apply. So you really don't want to be doing that for an 18-month lifespan. U.S. Bureau of Reclamation has been doing coating studies on the lower Colorado River for the last 6 years. Here is the website. I encourage you to read the results from Alanskaya for further details on that. There is also a very good estimate on how much it costs for non-foul release coatings. Again, here is the website to read at your leisure. Now, besides chemicals and coatings, there are at least 2 non-chemical strategies for keeping mussels out of your systems. One is definitely the use of filters. If it's a small system, something like a cartridge filter or a bag filter or a fixed mesh strainer will do quite a good job depending on the size of the population. What is the greatest particle size that should be allowed through such a filter really depends on where that water is going and how long that residence time is. So what I mean is, if you are filtering the water and then putting it into some kind of an irrigation pond where it will sit for, let's say, a week, even small villages that might get through will be able to develop, and at that point, you really have to start filtering down to the 100 micron size. If, on the other hand, you are filtering and then the water is going to be used within 20 minutes, then all you really have to remove are the largest villages that are ready to settle down in your system, and you can probably do very well with a 200 micron size filter. That is absolutely true for large systems that filter a lot of large volumes of water, where you need something like sand or media filtration or a mechanical filtration. Sand filtration has been used in a lot of irrigation systems. I see it on the edge of lots of fields to protect the distribution of drip lines from sediment. If they are protecting it from sediment particles, they will be protecting it from mussels as well. Large scale, it will really depend on the amount of total suspended solids that is in the water, because if the filters have to work very hard, you're losing a lot of water to backwash. Total suspended solids do vary during the year, so sometimes the filters will work better than others. There is a lot of mechanical filters out there which are self-cleaning. They all are basically more or less the same design. They filter down to whatever size you wish, and then they vacuum off the screen from the debris, and then they discharge debris during wet backwash while continuing to filter. They're very effective. They have been used in a number of different locations very successfully. What we have found to be the most important component of any of these mechanical filters is the screen. The screen has to be a square woven screen, which is very sturdy, stainless steel preferably, very well supported so that the vacuuming doesn't tear it. If the filter you're considering has that kind of configuration, it will probably do a good job. The last method that I wish to speak about today is the use of UV systems. They have been, medium pressure UV systems have been used in the drinking water industry for years. They have been used in the sewage treatment plants as well. And we had done some initial studies on biofouling control almost 25 years ago. It was very, very successful, but the UV manufacturer in those days were really not that interested in this market. Since then, because of ballast water, UV manufacturers have developed much more robust systems, and they are looking at biofouling as a good market. There is no chemical residue discharged from these, and they are very robust and efficient. How well they do depends on the transmissibility of your water. The more transmissible the water, the smaller system you need, the less power you need, the better it will work. Obviously, this is the life stage that the UV systems are after. It's the veliger stage. They are not able to really control the adult mussels that might be going through. Here is an example of a full-size medium pressure system from Atlantium Technologies that has been installed at a plant on the lower Colorado River to protect all of the cooling water on one of the units. The lamps can be changed while the unit is running, so there is minimal disruption to the operation of the plant, and it has been performing rather well. How well? This is just one of the counts that we do before and after the UV system. So in 1 month, we had almost 1,500 individuals settled per square meter ahead of the UV system. And after the UV system at 3 different locations, because we wanted to see if the veligers were actually recovering as they were going through the plant, we had less than 1% of the individuals that were present prior to the UV system. So it's very, very effective. And when you actually look at the performance of some of the strainers in the units that are and are not protected by the UV, there is a vast difference between the two, as you can see on this slide. And that's all I have, and I will be turning this over back to you guys.
Thank you, Renata, for that very informative overview. Now we're going to move into a couple of case studies. So our next presenter is Patrick Handyside. Patrick is a senior water management engineer with the Science and Technology branch of Agriculture and Agri-Food Canada in Guelph, Ontario. He started with AAFC in 2010 and started working with the LAD2 group, or LAD2 group, in the summer of 2011. In addition to the work he has done with this group, Patrick has also been involved in various projects looking at a number of issues such as improving water use efficiency through better irrigation scheduling, using controlled tile drainage to reduce nutrient loading to watercourses, while increasing crop yields and helping to improve water quality for dairy farmers that rely on surface water sources to meet their operational needs. So with that, Patrick, you should have presenter control now and should be ready to go.
Great. Thank you very much, Erica, for that introduction. And good afternoon, everyone, and welcome to my presentation. I'll begin with the outline for today's presentation. So first, I'll provide some background on the LADI. So they're 2 capitalized on that word. So it's LADI Group and their irrigation system. Next, I'll provide a quick lesson on dreissonid mussels, specifically with respect to their presence in Lake Erie, where the LADI irrigation system draws its water from. Next, I'll provide some details about why LADI is probably facing potential problems and the challenges they face with protecting their system. Next, I'll provide some detail on one of the treatment options that we explored for LADI, which is essentially lowering the pH of the incoming water. As part of exploring this option, we had to perform some preliminary testing, such as a mortality test using zebra mussels, in order to determine what our target pH should be, and then determining if this target could be achieved, especially at different flow rates and incoming lake water pH levels. Next, I would like to provide some detail on our sample collection and veliger identification program and look at LADI's risk for infestation. And then finally, I'll go over some of our future plans. So LADI, which stands for Leamington Area Drip Irrigation Incorporated, was formed just over a decade ago. About a dozen farmers and a few greenhouse owners came together to form this group, which from what I understand was a significant accomplishment in itself, given the nature of forming such a group among competing farmers. The group is mainly comprised of tomato producers who provide processing tomatoes to a few different processors in the Essex region around Leamington. The most prominent and best known of them was the Heinz Company of Heinz ketchup fame. At the time, these producers wanted to ensure that Heinz would remain in Leamington rather than pack it in and move to California, which was somewhat of a risk. And they thought that the best way to guarantee this would be to ensure that they could deliver high yields and high quality on a consistent basis, which could only be assured by having access to cheap and plentiful supply of irrigation water. So as part of their incorporation, they applied for provincial and federal funding, and thanks to their ability to justify that they needed a secure source of irrigation water to be successful, they actually received their funding. So once the agreement was worked out and the financial contribution of each farmer was determined, again, a significant accomplishment, construction of the Laddie irrigation system commenced, and the system was operational for the 2010 growing season. Now, unfortunately, Heinz did leave Leamington in 2013, but for other reasons. However, the departure of Heinz has had a minimal impact on Laddie's operations, thanks to the presence of other processors, including a company called Highbury Canco, which took over the Heinz facility in 2014. As I've already mentioned, most of the Laddie members are processing tomato growers, but they also grow these other crops in rotation, such as the corn, beans, and potatoes. Most of the greenhouses in Leamington, and there's quite a large concentration of them in that area, are vegetable producers, producing tomatoes, but not for processing. They also produce these other crops, such as cucumbers and peppers. So the map on the right shows the actual Laddie pipeline, total length in red, that thick red line, and the total length of which is approximately 36 kilometers. And the areas in green are the areas that service the system, which is greater than about 2,400 hectares. The system is divided into two branches, as you can see, a west branch and an east branch. So Leamington, that gray section there, just to the left of the line, is a small city of approximately 28,000 people. The city is located on the north shore of Lake Erie and is about 50 kilometers from Windsor, Ontario, which is sort of in the on the left and upper left corner side, and it borders Detroit, Michigan. So the system was designed to provide 7,000 US gallons per minute, but they were only approved in their permitting process to deliver about 6,300 gallons per minute. The filtration system for the system was designed to handle the max flow capacity and was sized to remove anything at 100 microns or larger, and that'll be something significant we'll talk about a little bit later. Since zebra mussels and related species have been in Lake Erie since the late 1980s, the engineering company that designed the system did incorporate some protection measures, such as the filters, especially since the majority of farmers will be using or are continually using drip irrigation. The intake pipe for the system, which extends approximately 150 meters out into Lake Erie, is located just off the shore of a local golf course, which is where the main pump house is situated. The large pipes inside the pump house are made of steel, but as they extend away from the pump house, they eventually become PVC, which is still very strong, but much cheaper. And they range from size from 24 inches in diameter all the way to 6 inches at the tap-off points. So the original design had about 61 tap-off points, but this number has since increased. Some farmers have their irrigation systems connected directly at these tap-off points, but most fill storage ponds from the tap-offs and irrigate from their ponds as needed. So there are two booster stations, a west booster on the west branch and an east booster on the east branch, and both are required to maintain system pressure up the respective branch lines. The inlet screen of the intake is coated with a substance described as Z-alloy, which is a copper-nickel material that was developed to repel resonance. This feature is inspected every spring as part of a yearly maintenance program. So the main pump house has 5 large pumps that are designed to provide a range of flows, from low flow that only requires 1 pump or to the maximum, which would have all 5 running at the same time. Since they are all frequency drive controlled pumps, the speed of the pump can vary to meet the demand, but still operate efficiently with respect to power consumption. So there are 2 banks. That second photo below the pumps shows that there are 2 banks of 14 Netafim disc filters sized to handle the low and high flows and designed to filter out anything that's 100 microns or larger, since, as I mentioned before, most of the farmers are using drip irrigation. So the original design of the Laddie system was that it was supposed to operate as a closed-loop system. What that means is the backwash from the Netafim filters was to be sent to a centrifuge where the physical parts, or the portion of the solids that are suspended, mainly algae and other suspended solids, would be separated and removed as solid waste. And then the leftover water portion would be allowed to re-enter the irrigation line before the Netafim to be used for irrigation purposes. Now, invasive resonance like zebra mussels were factored into the original design. The use of 2 dosing pumps, that's the bottom photo, You see one on the left, one on the right. So the two dosing pumps, one designed to inject chlorine into the intake line and one to inject chlorine into the irrigation main line past the net fin filters, was designed to provide chemical protection in addition to the physical protection provided by the net fin filters. So this next part will be somewhat of a review. I think we're going to probably end up seeing a lot of the same kind of slides for some of our presentations today. Dresinids such as the zebra and quagga mussel species are an invasive species that first appeared in the Great Lakes in the late 1980s. It's commonly accepted that they arrived here via the ballast water of ocean-going vessels, since they are native to the Caspian and Black Sea basins. This third species, though, the Conrad's false mussel species, is actually native to the Gulf of Mexico, but it can be found in some lakes and rivers in the north, but should not be confused with the other two species. So, as this map shows, the Great Lakes, specifically Lake Erie and Lake Ontario, as well as the St. Lawrence Seaway, have significant zebra and quagga mussel populations, which means they must provide an ideal habitat for these foreign invaders. So this image shows the different stages of the life cycle of zebra mussels. It's exactly the same image we just saw with Renata's presentation. It shows the formation of an adult zebra mussel from the fertilization of egg and sperm through the embryonic stage to the free-swimming larva stage, which then develops into a veliger larva. The veliger stage continues on until the end of the planktonic phase, when the veliger becomes a petaveliger. And this marks the beginning of the metamorphosis from a zebra mussel larva into an actual juvenile zebra mussel as it enters that benthic phase and is ready to settle. So the critical aspect of this is the free-swimming veliger stage and the effectiveness of those 100-micron net-fin filters at providing a physical barrier to the veligers from entering the Claudi system. So this slide shows what the environmental thresholds are for Dresinids to survive, or in fact to thrive. So again, as Renata has already showed, the calcium concentrations, alkalinity, pH, temperature, conductivity, etc., are all very significant factors with determining how likely you're going to have these individuals reside there. So these are some of the photos that have been taken at the Claudi pump house. Mostly juvenile zebra mussels that were trapped by a screen filter. So that's the top right-hand image. And then were collected on a filter cloth for a backwash. So that's the bottom. So it's sort of over like a top view, and you can see those are zebra mussel shells. Now, the photo in the top left, that's a photo that shows zebra mussels that were found on an inlet pipe in the pond of a farmer that uses the Claudi system. So it was concluded that they likely entered the pond through two possible ways. So one was that directly through the irrigation system early on during construction when there were no filters online, and the pipeline needed to be pressure tested. And this farmer is a board member, so he allowed them to pump directly into his pond. That's one theory. The other is it's possible that this farmer used a small boat or a canoe in his pond that was also used in Lake Erie. So as a note, no other mussels have been found in any other pond except for this one so far. This slide just confirms what the slide showing the distribution shows, and the other slide as well, that most of the Great Lakes provide an ideal environment for Dresinids, especially Lake Erie and Lake Ontario at the bottom. So this slide shows the average pH for Lake Erie as recorded at the Union Water Treatment Facility. Now, Union Water treats Leamington's drinking water. As you can see, the pH fluctuates between roughly about 7.5 and 9, but mostly stays close to that 8, pH of 8 mark. You can also see the impact of rainfall events and how it lowers the pH in the lake. This slide shows the average surface water temperatures for Lake Erie. Of particular interest is the time of the year that the temperature reaches 15 degrees Celsius, which is the ideal temperature for mature mussels to start breeding. This schematic diagram shows the layout of the pumps and filter systems in the main pump house. 5 main pumps are located on the left, and the 2 banks of Netafim filters are located just to the right of the pumps. However, this is a plan view, and the pumps are actually on the ground floor, while the filters are in the basement. The intake is at the bottom left corner, and the filtered water, once it passes through the bank of filters, exits the pump out to the top right of the filter banks. And this is both those, the inlet and the outlets, are in the basement. So the original system was designed as a closed loop system where backwash from the Netafims could be added back into the system. However, this system failed because the centrifuge did not work properly, and the amount of suspended particles remained very concentrated in the backwash. Therefore, to prevent the system from going into a constant backwash loop, the backwash line had to be reconfigured, and in fact, it was redirected back to the lake. So as a result, no chlorine could be injected at the intake, since there was a risk that residual chlorine would then enter Lake Erie, which is not permitted according to the Ontario Ministry of the Environment. So therefore, the Claudi group had to reevaluate their options for effective yet safe treatments. So one option, which actually the Ontario Ministry of the Environment did not disapprove of, was the use of phosphoric acid to lower the pH of the incoming lake water, which would impact the development of dresnids since their shells are comprised mainly of calcium carbonate. So the goal was twofold. One, to prevent the development of villagers, thus preventing them from settling, and 2, killing off settled adults, as they would succumb to the effects of the low pH environment over time. So as a way to monitor the effectiveness of the Netafims and assess the possibility of villagers getting past them, bioboxes were used to monitor the raw, unfiltered lake water coming in and the filtered or treated water that was going out. So a mortality test was conducted to help determine our target pH. So we looked at 5 different pH levels to help determine a reasonable dosing rate. Each environment started with 10 zebra mussels, and the pH was monitored and corrected throughout the day over a 6-week duration. The zebra mussel habitats were checked for, for dead mussels daily. So this chart shows how successful the low pH environments were at killing off mussels over a relatively short period of time, which is on the left. And while the lower pH environments on the right took a bit longer, but did eventually cause mortality. So as a result of the mortality trial, we determined that an acid injection trial should be conducted, where we could try to maintain, and we came to, and obviously this number we've seen before, and it was through Renata's help with this, that we came to the conclusion that we wanted to maintain a pH of 6.9. So an acid injection curve was developed, which showed us what acid dosing rate was required to achieve a desired pH, in our case, pH of 6.9. So rather than using 85% concentrated phosphoric acid, we chose to dilute it to 40% concentration and minimize the corrosive impact on the equipment, such as the plastic tubes and actually the dosing pumps themselves. So 2 trials were conducted, one in November 2011 and the second in June of 2012. So this is a curve that was developed as a result of our trial. So, for example, using this curve, we can determine that for every 100 of gallons per minute of lake water, that we had to use, so at an initial pH of 8, so if we go to 8 on the x-axis and go up where that curve intersects that line and go across to the left, we'd need to dose 0.75 liters per hour of a 40% phosphoric acid solution in order to maintain a final pH of 6.9. if the initial pH of the lake water was 8. So this chart shows the results from the 5 days of testing in November 2011. Each day had different starting lake pH levels and different flow rates. So with the exception of day 3, we were able to reduce the pH of the incoming lake water and hold it relatively close to our target pH of 6.9 under both high and low flow conditions. Not sure what was happening on day 3. We might have been having trouble dealing with the buffering capacity of the lake that day, though. So there's a lot going on here. Sorry about that. This chart shows what was happening on one of the days of our second acid trial that took place in June of 2012. So the trial started at 1 p.m. and ended at approximately 11 p.m. So the blue zigzagging line at the bottom represents the flow over the course of that period of time as recorded by the main flow meter. You can see how it fluctuates over the testing period. And then obviously later in the evening or later in the day, obviously flow rates start to drop off. You don't need as much irrigation water as the sun goes down. So the thin red line at the top shows the pH of the incoming lake water, which is also fluctuating slightly. The orange line shows the pH of our monitoring system, which records the pH just after the acid injection point. And the bluish-green line shows the pH measured by a probe located at the West Booster Station, which is about 6 kilometers down the line from the main pump house. Hence the lag in pH at the start of the trial and at the end when the acid dosing pump was turned off. This chart shows the approximate monthly and yearly cost of phosphoric acid to meet our pH target of 6.9. At the time of testing, it was estimated that it would cost approximately average 14 cents per 1,000 gallons of water pumped. So for 2013, 14, and 2015, villager sampling was conducted at the Laddie Pump House to assess the protection provided by the Netafim filters. Water temperature was also monitored starting in May, just as water temperature started to approach the 12 to 15 degrees centigrade. So water samples were collected from raw and filtered sampling ports, and a plankton net with a 20-micron filter was used to collect samples. Using prepared samples, observations were made using a cross-polarized light microscope. So these two photos show the appearance of villagers in 2 separate samples. In this case, there are much more villagers, thankfully, in the sample taken before the filters versus the sample taken after the filters. Again, there's a lot going on in this slide. So this slide shows that the Laddie system, both the intake line and the network beyond the Netafim filters, were at a very high risk for dresinid infestation starting on June 20th, 2014, and throughout the summer months and into the early fall period. So the red line, which is where you see the first 2 large steep peaks, is the raw water and the population of villagers that we counted in that water starting in that time period. And then you see, after that period, you see there's the water in the filtered water. We're starting to see villager numbers starting to increase throughout the year. So going forward, we'd like to continue working with the Laddie Group and monitor other aspects of their system, such as using monitoring equipment like the bio boxes and collecting water samples in the booster stations and at the top tap-off positions at each farm, and then look at monitoring ponds for signs of adult mussels. I'd like to thank all the people that were involved in this, my colleagues at Agriculture and Agri-Food Canada, the Laddie members, Union Water, and Renata, you're here today. Thank you very much. And thank you for your time today.
Thank you, Patrick. We're going to continue to hold questions till the end of the webinar and move on to our next presenter and case study. Our next presenter is Barry Olson. He is a research scientist with Alberta Agriculture and Forestry in the Irrigation and Farm Water Branch in Lethbridge, Alberta. He has been with the department for 22 years, carrying out applied research on agricultural environmental topics, including manure management, phosphorus, groundwater, and evaluation of beneficial management practices. So Barry, you are the presenter. It looks like we're seeing your presenter view. I don't know if you can switch to your other monitor. There we go. Perfect. And you should be all set to get started.
Thank you. Thank you very much, Erica, and good afternoon, I guess, to most people. And I'd like to thank the organizers and the Great Lakes Commission and the Invasive Mussel Collaboratives for this opportunity to present on some of the work that we're doing in Alberta with respect to irrigation. First of all, I'd like to acknowledge my co-authors, Andrea Kalschuk, Brad Calder, Kiao, Lloyd Healy, also with Alberta Agriculture and Forestry, and Ivan Friesen, who is the General Manager of the Eastern Irrigation District in Alberta. Okay, you've seen this map already presented by Patrick. Just showing you where relative to Alberta, shown in green there in the upper right portion or upper left portion of the map. And of course, as we all know, the spread of mussels has been occurring for the last few decades here, moving south and moving towards the west. Of course, Alberta and the surrounding provinces and states have been free of mussels for the most part. Of course, the alarm bell started to ring when mussels moved into Manitoba 4 years ago. And that's when the activity in Alberta started to ramp up, and the government and stakeholders started to take action in terms of inspections and education and so on. Of course, things got even more concerning when villagers were detected in Montana, just south of us. Of course, our sister branch, our Department Environment and Parks, they assess the chemistry of water in Alberta and in most of our lakes, and most of our lakes would be very conducive to a mussel population if they should get into the province. Now the detection in Montana late last year, like I said, made us more concerning. And because Alberta is hydrologically connected to Montana, we have a couple of rivers flowing from Montana into Alberta. Plus, of course, there's the border crossings. We have at least six border crossings in Montana, and there's of course a few into Saskatchewan as well. So certainly that boat traffic is coming in from Montana to Alberta is of course of concern. Now, I haven't been given any background on mussels in themselves because I felt it would probably be covered by other presenters, so I thank you very much for doing that. I'll just move into why is it a concern, particularly from agriculture and irrigation in Alberta. Well, of course, southern Alberta has a very large, very modern, and very efficient irrigation system that has been built up over many decades. It is currently the infrastructure is currently valued at nearly $4 billion. It includes 51 reservoirs, 3,700 kilometers of canals, 4,300 kilometers of pipelines, the control structures, pumping stations, and there are 13 organized irrigation districts in addition to private irrigators. So we have a very large system throughout the southern part of the province, which certainly provides a significant flavor to the agriculture in this part of the province. And of course, the irrigation infrastructure supports irrigated land. We have about 700,000 hectares of land, which supports a wide diversity of crops that couldn't otherwise be grown here, and of course, increase the yield production. It also supports the livestock industry, particularly the confined feeding operations in various parts of Alberta in the south. It also provides water to a variety of communities and municipalities. It supports wetland development and maintenance, as well as parks and recreational activities, particularly around the reservoirs within the irrigation system. So of course, Alberta is still mussel-free, but of course there is this great concern, and this is why Alberta Agriculture and Forestry has been very involved in the last 3 or 4 years, as well as our irrigation stakeholders. when they became aware of the immediate threat, they certainly were very concerned about mussels getting into the irrigation infrastructure, and the irrigation districts and the irrigation industry in general have been very involved with the preventative aspects of the program in terms of education and supporting the inspection aspects that's been carried out by Alberta Environment. But of course, they ask the question is being very practical, is that, well, what if mussels do get into Alberta? What do we do? What are our options? So of course, if that does become the case, how do we control mussels? So we looked at the various options, and Renata gave a very good background on various aspects. But considering the size of our system, diversity of our system spread across the southern part of the province, we felt that probably a chemical control would be probably the best option. So we pretty well have been focusing on that. So we looked at the various options that are available out there in terms of chemical control. So we looked at the various aspects of which chemicals to maybe pursue in terms of availability, cost, effectiveness, and of course, very important, what potential negative impacts it may have on the environment. And of course, health and safety in terms of using these chemicals. So doing this type of an assessment, we decided on using potassium chloride, or in the form of potash, as our chemical of choice, if you like. And the other note here I want to make is that there are no chemicals currently registered in Canada for the control of mussels to the scale that we will want to use. So why potash? And again, Renata mentioned some of these things. That it affects the it acts as an anesthetic against the mussels. We believe it interferes with the gill respiration. Potash is naturally occurring. It's an essential nutrient for plants and animals. It's available locally in large quantities. Our sister province to the east, in Saskatchewan, has large reservoirs of potash that is currently being mined, and so it's relatively easily purchased. And most of the potash that is mined is used as an agriculture fertilizer. So what we're doing in terms of, we're actually pursuing the registration of potash as a control for mussels, and this is being led by Alberta Environment and Parks, with assistance from Alberta Agriculture and Forestry, Alberta Innovates, and one of the manufacturers of potash, Agri-Food, is on board with this effort. So we're working with the Pesticide Management Regulatory Agency, which is part of Health Canada. We've already submitted a pre-submission back in 2015 and 16, and from that response, we are now currently preparing a full registration application, which we hope to submit later this year. Of course, this can be a long-term effort. So we are moving forward and trying to get potash registered as a chemical for mussel control. Now, what I want to focus on is some of the work that we're doing, because to kind of address that question that the irrigation districts have asked, is, okay, what can we do? And like I say, we focused on using potash as a means of control. So we need to do some work on, okay, how do we use this product as a control measure? So we've set up a started a research project last year, and with 4 objectives. One is to develop and test potash preparation methods, develop and test the pipeline injection equipment and methods, assess the effects of irrigating potash treated water on soil and crop health, and to confirm the economic costs and consideration for treating Alberta's irrigation systems with potash. And this will be a very important stage of this research, considering the large-scale system that we have to deal with in southern Alberta. But what I'm going to focus on for the remainder of the presentation are objectives 2 and 3. This research has a number of partners. Of course, Alberta Agriculture and Forestry. We're successful in obtaining some funding from the Growing Forward 2 and Alberta Innovates. The irrigation districts, particularly the Eastern Irrigation District is involved in this project, as well as the Alberta Irrigation Project Associations, and Alberta Environment and Parks also has some involvement with this project. So I'll just describe some of the efforts that we did last year. One is the pipeline field trial, and we were able to carry out one test in the Eastern Irrigation District last July. And then we also established a small plot study at the Alberta Agriculture and Forestry Irrigation Technology Center, which is located near Lethbridge, Alberta. So first of all, just a description of the pipeline system. So we were very fortunate that in the Eastern Irrigation District, they were able to find a pipeline system that was perfect for our first trial, because it was a very simple pipeline system. There was a small pipeline from the main canal filling a settling pond, and this fed a 2.5 kilometer long pipeline which serviced one field. So it was an ideal simple system, straight pipeline and one field to deal with, and this was a quarter section, or the pivot area was about 40 hectares in size. This trial was carried out in early July of last year. So this is a schematic just showing the arrangement with the settling pond on the left-hand side, the 2.5 kilometer pipeline, and then the irrigation system, which was a center pivot system. And with the pivot on, the flow rate through the pipe was a little under 3.5 cubic meters per minute. At the inlet of the pipe, there is a air vent, a vertical air vent pipe, in which we injected the potash solution that was prepared. And the potash solution was prepared at a concentration of 112 parts per million, or milligrams per liter of potassium. We used a pumping system to inject the potash stock solution into the pipeline, and we were applied the potash at a rate such that we would obtain a 100 ppm of K in the water, which was our research target concentration. After the pipeline was completely filled with the treated potassium, then we shut down the pivot system and then closed the inlet to the pipeline, and then we held it for 48 hours, or two days. And this took us about a little under 2 hours in order to fill up this relatively small pipeline system with the treated water. And we sampled water throughout the system to see whether or not we obtained the concentration that we wanted to, and to determine whether or not that concentration was maintained over the 48-hour period. And we were successful to do that. Actually, we reached a steady concentration of 106 milligrams per liter, and we were able to successfully hold it in the pipeline for the 48 hours. Now, the other thing that we are concerned about is applying the potash treated water onto agricultural land, even though it is a fertilizer. But if we do go into a maintenance mode, we may have to apply it on several times. So after the pipeline was charged with the potash solution, we then went and sampled the part of the field that would be receiving the potash solution 2 days later. And then after the potash solution was applied to the land, we then went back and resampled those sampling points. So we took 10 samples in a transect in the area where the potash was applied. And we sampled the soil in the 0 to 15 centimeter depth. And in this case, the volume of water that was in the pipeline, it required us to apply the water on an area that was little under 5 hectares in size. So it was about 1/8 of the size of the field that received the potash treated water. And what we saw was there was essentially no effect on the soil chemistry that we measured in terms of extractable potash. There was no effect between the pre and the post. The chloride in the soil, again, there was no statistical effect. And even though electric conductivity seemed to be popped up a little bit, statistically there was no significant difference between the pre and the post soil samples in the topsoil layer. Now, just to compare, what we used was about 74 kilograms of KCl in order to treat the pipeline, which is equivalent to 39 kilograms of K. The amount of water that we applied onto the soil was 55 millimeters. So this worked out to be about 8 kilograms per hectare of K was applied. And if you compare that to the canola field that was growing on that field last year, and you assume an average yield of about 2 metric tons per hectare, that crop would remove about 17 kilograms of K per hectare. So certainly the amount of K that we applied was much less than what that crop would have removed. And if you compare that to the application of beef manure, which also contains a lot of potassium chloride, moderately high level of beef manure application, the same 65 metric tons per hectare, would deliver 700 kilograms of K per hectare. And the practice of applying beef manure in southern Alberta is quite common. So just to put that into perspective. Now moving on to the small plot study. Now, of course, the previous pipeline study we did, that was only a one-time application at a relatively low rate of irrigation water being applied. So the purpose of the small plot study was to look at, okay, what if we have to apply the potash on a repeated basis in order to maintain the system? So we set up 3 treatments: a 0 without any potassium, 100 ppm, which was our research target concentration, and then we also put in a high rate as well, at 500 milligrams per liter of potassium, and the treatments were replicated 4 times. And last year we weren't able to apply the treatment until late in the growing season, but we did apply it 3 times, and each time 15 millimeters of irrigation water was applied. And at the Irrigation Technology Center, we had access to a experimental or a small plot pivot irrigation system, a 1-span pivot irrigation system, which is shown in the photograph at the bottom there. So the arrangement of the plots was in a circular design because of the pivot irrigation system. So the circle is divided into 4 quadrants. Each quadrant, the treatments were randomized in each of the 4 reps. And last year, barley was the test crop that was seeded. Now, within the large pie-shaped portion treatments, we measured out 3x3 microplots, and it was from these microplots where we selected or sampled our soil samples. So the application rates at 100 milligrams per liter of K applied 3 times, each at 15 millimeter volume or depth of water applied. We applied 45 kilograms of K per hectare, so that's certainly quite a bit higher than what which we saw at the pipeline trial. And at 500, of course, would be 5 times that rate. So again, 225 kilograms per hectare of K. So certainly the amount of K that we're applying here is considerably higher than what we saw in the pipeline trial. The results that we found at the 100 milligram or parts per million of K, we found that the K, the chloride, and the electrical conductivity increased in the surface soil, but they were not statistically significant. However, at the 500 milligrams per liter of K, the K also increased in the surface soil, but again, not significantly, but chloride and EC significantly increased in the surface soil. And we also saw that with depth, the chloride leached further into the soil. So in terms of future work, we want to continue some of our potash preparation, and we'll continue to modify our methods, which I didn't discuss today. The pipeline field trials, we want to move on to more complex pipeline systems, and our goal for this year is to test four systems in not only the eastern irrigation districts. Some of the other irrigation districts will also be participating in these trials in the coming year. So we want to get much more complicated branch line systems, maybe up to 5 to 20 irrigation systems within these pipeline systems. We want to use a new pump and flow metering system, so we want to try and automate the injection process, because when you have multiple irrigation systems on a pipeline system, some will be turning off and turning on, so the flow rate's going to vary as we charge the system with the treated water. And also look at the soil chemistry and crop quality, which the latter we weren't able to do this past year. And a small plot study, again, repeat the applications, and this year we'll get things started a little bit sooner and apply it maybe up to 5 times during the season. Again, look at the soil chemistry, but also look at the crop yield and quality as well. And then our fourth objective that we have for this project is to do that economic assessment, and we hope to begin a contract work on this in spring of this year. So with that, that's some of the work that we've been doing in terms of the issues around irrigation in Alberta, and some of the efforts that we're trying to determine how to protect the irrigation system if mussels should get into it. So I'll turn it back to you, Erica.
Thank you, Barry. We have one more presentation, and then we'll get to your questions and answers. Our final presentation is from Bridget Gruber. Bridget has 8 years of experience in aquatic invasive species research and management, and is committed to bringing a sensible solution to the invasive mussel problem. She was trained at the University of Michigan as an aquatic ecologist, and previously she worked as a molluscicide researcher and pesticide project manager for a biopesticide company in California. And Bridget's presentation is focused on a new technology and development that could have applications to irrigation system. So Bridget, you should be all set to give your presentation.
Okay, thank you, Erica, and thanks everybody for joining us today. Like Erica said, I will briefly, I know we're getting short on time, so I'll briefly go through this new product that we are developing, we being ZM controllers. And Renata did a really excellent job of talking about pH adjustment as a means of control, and that's pretty much the idea behind the ZMX, this new biochemical dracaenic control technology that I'll tell you about. So I'll quickly go through what is ZMX. I'll share some efficacy data that we have with you, and then I'll talk very briefly about the potential benefits of using ZMX in irrigation. So what is ZMX? This is a management option for closed systems. We, ZM controllers, have patent pending status for ZMX, and I'll again elaborate on what exactly ZMX is. It's compatible with most materials and safe for workers, and this next point is pretty significant for us. It's exempt from U.S. EPA registration under the FIFRA 25B legislation, and FIFRA 25B lists a number of reduced risk chemicals that U.S. EPA deems so reduced risk that those products do not need to be registered as a pesticide. So one of our formulations is a citric acid formulation, and it falls under that FIFRA 25B, and so we don't have to go through the very time-consuming and potentially expensive process of registering. We are, however, in the process of registering 2 other formulations that are not under FIFRA 25B, and we're also in the process of registering in Canada. ZMX is environmentally sound, and you'll kind of understand why as I go through this presentation, and it is scalable. It's currently being manufactured at large scale, so it's scalable and it's readily available. And so as Renata mentioned, invasive mussels have a narrow range of pH tolerance and a minimum required level of calcium. So ZMX depresses pH with organic acid. By manipulating the pH with these specific organic acids, we can control the mussel survival and settlement. So depending on the management goals or strategy, as I think Renata put it, be it proactive or reactive, if you're looking to remove settled mussels or if you're looking to prevent settlement, we can work with that. We can accommodate those different, ZMX can accommodate those different management goals and be used in those different treatment scenarios. So in the case of preventing settlement, less of these organic acid blends can be used to target a pH of under 7 for longer periods of time. Or if you're looking to remove settled mussels, we would use more ZMX to target a pH of around 4, and that would very quickly remove the settled mussels. So like I said, we're highlighting the citric acid as our sort of flagship ZMX product right now because we have noticed it's very highly efficacious in our lab testing that we've had done, and I'll show you some of that data. It's readily available. You all probably know what citric acid is. It's used in other applications, so it's commercially available, large scale, and very importantly, it's exempt from EPA registration under Fit for 25B. There are a number of states that defer to this Fit for 25B exemption. I'm aware that California, Minnesota, and Texas are some of those states, meaning we don't have to go through the registration process at the state level either. We would still go through the registration process in the other states, but state registration processes are typically much less expensive and time-consuming. So we're focusing on citric right now, and I'll talk a little bit more. I'll expand on the citric applications. So does it work? We know that the registration process is pretty simple at this point, or it's exempt. It's readily available. We all kind of know what citric is, but does it work? RNC Consulting, Renata, who we all heard from already, did some initial lab tests for us back about a year ago. And we saw that we got 100% adult mortality in about 3 days in warm water, so water that was warmer than about 18 degrees. This was done in Ontario water, so depending on the background water, the water chemistry will dictate how much ZMX needs to be used in order to get to the targeted pH. In this case, we were targeting about 4 pH, so we used 250 ppm of the organic acid blend. And within 3 days, we saw 100% mortality. She also did some tests in colder water, so around 10 C, and with that same 4 pH target, about 250 parts per million of the organic acid blend. Within 14 days, we saw 100% mortality, which is comparable and in some cases faster than current chemical technologies, particularly the oxidizing chemicals. And if you'll notice here, too, at about day 11, we were seeing pretty close to 100% mortality. So encouraging results. We also had some testing done by Kelly Stockton Feedy, KASF Consulting in Nevada, on using veligers. The idea here, we were kind of exploring the option of using ZMX as a decontamination tool. So at this point, we were trying to see how quickly could we kill veligers in a standing water situation. So, for example, standing water on a boat. Could it be used as a decontamination tool to kill veligers very quickly? And so in this case, we used 2% citric acid and 0.6% citric acid. And within 5 minutes, we saw 97% mortality of the veligers. So we think with some development here, we have an interesting application possibility, a decontamination or potentially development for transfer water decontamination. More research needs to be done, and I'll mention a little later in my presentation, we are looking for partners because we are in R&D phase and we want to do some more field testing and some more demonstrations. So I know we're focusing on irrigation today, so I'll mention some of the benefits that we think ZMX could have in irrigation. We have an agronomist on our team, and so he's sort of targeting this application. And based on the literature out there, if ZMX is used in irrigation, it could potentially reduce parasitic energy loss by inhibiting and removing scale, stimulate crop growth by converting the insoluble minerals into fertilizer, reduce biofilm, positively impact soil characteristics, and therefore promote healthy soil microbiome, which therefore may decrease soil pathogens. It sounds like there's a lot of agronomists on the phone today, so this may all ring true or sound encouraging for you. But again, this is all based on the literature, and we are looking to do some more testing and some more demonstrations. So if that sounds like something you would be interested in, please reach out to me. And like I said, we're seeking research partnerships. I know there are funding opportunities out there. If anybody's interested in partnering with us so we can get some more data, like I said, we are in the R&D phase. There are about 4 of us on the team right now. we've been doing this on a shoestring budget up to this point, but we're passionate and excited about what we've seen so far. We just need to take this next step and do some field testing and get some demonstrations under our belt. So please send me an email, reach out to me, and we can talk. But that's all, Erica, so I'll hand it back over to you.
Thank you, Bridget. We do have a few minutes left in our scheduled time today to answer a couple of questions that we received. The first question I'm going to direct to Renata to start with, and then open it up to the other presenters if they have any experience with this. So Renata, the first question for you is, has anyone looked at using a weak electrical current to keep mussels from attaching to piping? Hold on one second, Renata, we may still have you on mute. There we go.
Oh, sorry.
Renata, I'm sorry,
Okay.
Could you start your answer again?
Yes, there has been some research in this area, and we have seen some effects, but we have not been able to translate that into a commercial installation. So we know that certain levels of impressed current will keep mussels off of metal surfaces. We also know that putting a metal mesh over concrete and electrifying it will also prevent some settlement, but it has been very difficult to get reproducible results, and basically this research was done quite a while ago, and nobody has pursued it. I know that in Texas they are actually looking at cathodic protection on their gates to see if it actually is keeping mussels off of their gates, and I haven't had an update on that project. All I've got.
Great. Thank you, Renata. Patrick, Barry, or Bridget, if you have any experience or knowledge about looking at electrical current?
This is Patrick. No, I do not have anything to to add for that.
Barry
I don't
here.
either.
We have no I have no experience in that, and if it sounds like it has to be a metal surface, so most of our, in fact, all our pipelines that's being installed in the irrigation system in Alberta are PVC. So.
All right, thank you. Our next question I'm going to direct to Patrick first, since I think it came in during your presentation, and then open it up to the others. So Patrick, can you talk at all about the cost of potash that was used?
We did not use potash in the work that I did. It was something we had considered, and in fact, it would be something we would consider for treating if we did find zebra mussels in ponds. I did do some work into that and cost analysis for that, but I don't have those numbers in front of me. So perhaps Barry, you might be better positioned to answer that one.
Yes, I can. We've done a little bit of. We keep track of our costs, and and certainly with our economic assessment that's coming up, we'll be able to have a better assessment of that. Now, the potash that we used for the pipeline system that we tested last year, we only used about, I think it was 74 kilograms, and the cost of potash at that time was about $550 per metric ton. So I would work out to about $40 for the product itself. But of course, there'll be a lot more other expenses in terms of the cost of actually applying it and the equipment and stuff like that. So.
Great, thank you, and thank you for clarifying that. Barry, I'm going to go back to you again and follow up with another question about potash. So we had a question, are perchlorates a concern with potash?
No, I don't think so. We're not too concerned. I know there's some additives in the potash in terms of preventing the dusting and caking and stuff like that. But no, we're not too concerned about that right now. But again, we're working with the registration process right now. We'll be finding out if we need to do some work in that area.
Great, thank you. I'm going to go back to Renata again, and then open it up to others if you have anything else to add. We also had a question if anybody has looked at the use of ultrasound as a control option.
Yes, ultrasound was investigated when the mussels initially came into the Great Lakes. Again, there is a definite reaction to ultrasound. The problem we had was getting repeatable results. Temperature of the water, currents are all variables. So although we did do a couple of experiments using various ultrasound generators, we were not able to actually show that they were particularly effective or reproducible at the time. So again, a branch of research that was not really followed up greatly after that.
Thank you. And it looks like we have just one more question about another possible control method. And so we had a question, how effective is water turbulence at killing veligers and or adult mussels? Okay, well, I will take that. And there is a lot of controversy around turbulence as a way of control. There is no doubt that certain turbulence conditions will result in mortality of veligers. But I would like to point out that there is many power plants around the Great Lakes and Lower Colorado River which are using various ways of pumping them and creating huge amounts of turbulence and various shear stresses and pressures and so on. And unfortunately, the mussels do seem to be able to survive that. Perhaps not all of them, but certainly enough of them to cause a problem. So I am not discounting turbulence as a potential means of control, but we have, in practical way, we have not seen it as something that had a huge effect in existing structures. Great, thank you. So we are just at time here for our allotted time for this webinar today. I did want to give each one of our speakers one last chance to say anything else before we conclude. If there are any other key take-home messages or lessons learned you wanted to convey before we wrap up. So Renata, anything else you wanted to say this afternoon?
No, I think, I stress to all the clients that knowing your water chemistry is very important. It is the key to successful control in so many ways. And the mussels are not invulnerable, although sometimes they look that way. And so don't panic.
Thank you. Patrick, anything else you wanted to add before we wrap up?
Well, no, I'll just say this, Erica. I just want to take the opportunity to thank the Invasive Mussel Collaborative for allowing me to give my presentation today. And I guess if anyone does have any further questions, they'll have my contact details to get a hold of me.
Great, and thank you. Barry, anything to add?
About the same as Patrick. Thanks for this opportunity to share what we're doing in Alberta. We're still at the very early stages in terms of developing a defense in terms of if mussels do get into our irrigation system. So we're certainly looking to others to learn from their wisdom and so on. And again, my contact information is in the presentation. So if anyone want to get a hold of us to find out more details, please do so. Thanks.
Thanks, Barry. And Bridget, any closing thoughts from you?
Thank you, Erica and the Invasive Mussel Collaborative and the audience for hearing me out. And again, if anybody is interested in partnering with us to do some field testing or some demos, please be in touch.
Great. And I will just close by thanking all of our presenters once again and our participants today. As a reminder, this webinar was recorded and will be posted on our website in the next day or two. And if you have follow-up questions or comments, please follow up with our staff here or any of our speakers. Thank you, everyone.
Thank you, Erica.
Thank you.